this morning's session. So it's my pleasure to introduce to you Francesca Arici, who will talk about a non-commutative approach to the topology of circle and sphere bundles.
Thank you very much. And yeah, thanks also to the other organizers for the invitation to talk at this conference. I was really hoping to be able to attend in person, but yeah, it looks more complicated than expected. And it's very nice to have those events happening. So I'm going to talk about some line of research that I'm working on at the moment, which deals indeed with a slightly different type of quantization than what we saw so far in the talks. So it will be mostly about the idea that operator algebras and sister algebras, so particular classes of algebras, can be seen as quantum versions of classical geometric and topological objects. So I'm going to start with that and then move into indeed the discussion of how to study the topology of sphere bundles, which are a huge class of topological manifolds with extra structure that are particularly interesting in algebraic topology and other applications. So I'm going to start with this kind of philosophical slide where I put here a quote by Sophie Germain. This quote is about the idea that whenever you do algebra, this is the same as doing written geometry, and geometry is figured algebra, so algebra you can draw. And this sentence that is a couple of centuries old is actually the general philosophy of much of what has been happening in research in mathematics, in particular in various types of geometry. And we often refer to it as a duality between algebra and geometry. And it dates back to work of other mathematicians like Descartes when he introduced the coordinate system. And of course, this idea was brought forward to a greater extent in the early 20th century by Noether, Hilbert with the Stellensatz and the Basissatz that tell you that there is a correspondence between polynomial equations and algebraic varieties. So algebraic varieties are set of zeros of polynomials. And whenever you have algebraic variety, you can recover polynomials by looking at the radical. And this whole idea that you can connect algebraic properties to geometric ones, and that you can try to answer geometric questions by solving corresponding algebraic problems was of course brought forward by Grothendieck in his work of reformulating the whole set of axioms and structures of algebraic geometry. So this is something we are all quite familiar with, but I would like to talk about a different type of duality, which is more topological in some sense, and that's what is known as Geoquant duality. So the starting point will be a compact Hausdorff space, so compact topological space, such that the topology is Hausdorff. And to this space, we can associate an algebra. We will see this is an algebra, but at the moment it's just a vector space or a set if you want. C of x. C of x is the collection of all continuous functions defined on x that take complex values. And this, in principle, set comes actually with a much more extra structure. So first of all, it has a vector space structure. And this vector space structure just tells you that whenever you have two functions that are continuous on x with values in the complex numbers, and whenever you have a complex number, you can use it to define linear combinations. So the function lambda f plus g is the function that in the point x takes a value lambda times f of x plus g of x. So this is a vector space structure that is defined pointwise by exploiting the natural vector space structure that you have on the complex numbers. There are other structures on the complex numbers that we can bring to our set C of x. So C of x comes with a product that is commutative. Indeed, whenever you have two functions f and g that are continuous complex valued, you can define the product function f times g by setting it as to be the function that in the point x has the value that is the product of the values of the two functions. And this gives you a well-defined product that, of course, because the product in the complex numbers is commutative, then the product of functions will also be, because it only looks at the pointwise structure. The set C of x also has a unit for this product. This unit is a function that is identically equal to 1. So at every point in x associates the points 1. This is continuous because x is compact, so there are no issues there. And this set also comes with something that is called an involution, which is a map that when applied twice is equal to the identity. And this involution is again defined pointwise, taking the involutive structure that the complex numbers have. So f star of x is equal to f of x, so the value of f in x complex conjugate. Now, all this comes together in a nice algebraic way, and there is compatibility between the involution and vector space structure and the involution of the product. But in particular, this makes it not just algebraic. If you introduce something else, if you start putting analysis into the play, you have even more structure. So on this space C of x, there is a norm, and this norm is defined to be the supremum norm. So the norm of the function f is just the supremum of all the values that the function attains on the set x. And if you look at this C of x with this norm, this set that has the structure before being an algebra with an involution that is compatible with the algebra structure is actually what is called the Banach-Star algebra. So it's also complete with respect to the topology that is induced by the norm. Banach-Star algebras are a big class of algebras that you can study in analysis, but this particular algebra, C of x, has an extra property that is known in the literature as C-star identity, which tells you that whenever you take the norm of the product of f star and f, this is actually equal to the square norm of f. And this is not a given in general Banach algebras. Of course, there is one direction that is always true, which is that the norm of f star f is bounded by the square norm of f. But in general, the equality may not be attained. So whenever Banach-Star algebra has this additional property, it's called a C-star algebra. And our algebra in question, C of x, is in particular a commutative C-star algebra because we saw that the product that we define is the pointwise product is actually commutative. So I'd like to give you a very simple example of commutative C-star algebra, which also shows that the C-star norm is, the C-star identity is quite restrictive. So you can look at the set of endpoints and look at the continuous function on a discrete set of endpoints, and this will be isomorphic to the space C of n, so to the n-dimensional complex vector space. And this is a C-star algebra with the usual vector. Well, it's a star algebra with the usual vector space structure, coordinate-wise multiplication, complex conjugation. But in order for it to be a C-star algebra, so for it to satisfy the identity that I boxed in my slides, you actually need to choose a suitable norm. And a Euclidean norm does not satisfy this C-star identity. The right norm that you have to choose to have the C-star identity is the supremum norm. So it's a norm that you define as the square. So you define the norm of Z1, Zn squared to be the maximum of the products of Zi with its complex conjugate. And this is different than the Euclidean norm. And you can think about it as the norm that the operator norm of the matrix that you would get by putting the entries of your vector on the diagonal. And this is the only norm, the unique, actually C-star norms are unique. That is the unique norm that makes C of x, that makes C of Cn, so the n-dimensional vector space, over the complex number, a C-star algebra. There are many norms you can put on that object, but there is only one that satisfies the C-star identity. Okay, so actually, the nice thing about this construction, the fact that you can associate to every topological vector space a commutative C-star algebra, is that you can also do the other way around, and that you can recover the information on points of your space. So any point in your space X can actually be thought as a functional on C of X. So a function defined on C of X. And this functional is defined by taking a function f and evaluating it in the point P. Now those functional clearly are multiplicative because of how our product of functions is defined. Indeed, if you look at sigma P applied to the product function f of g, this is f of g computed in P, and we know that f times g in P is actually the product of the two values. So you get that this will be equal to sigma P of f times sigma P of g. So the function is multiplicative, and when you apply it to the function that is identically equal to 1, that gives you 1 because that's the value of that function in any point. So whenever you have a functional on an algebra that satisfies those two properties, you say that it is a character. And it's an important result in the theory of sister algebras that all characters on C of X, on the commutative algebra C of X, are of this form. But the even more important result is that the set of characters that we often call the spectrum of the sister algebra is actually a topological vector space with respect to a certain topology. And it turns out to be homomorphic to the topological space you started from. So in particular, you can use this information to prove an essential theorem that was proven in the 50s by Gelfand, which tells you that whenever you have a commutative and unital sister algebra, this is actually, there will always be a star isomorphism between the algebra A and the algebra of the continuous function on its spectrum. So on the set of multiplicative characters or pure states. And this is a star isomorphism of a commutative sister algebra. So it respects all the structure and respects the star structure compatible with the norm. It's actually isometric because it's an isomorphism. And this is somehow at the basis of non-commutative geometry or non-commutative topology, if you want to be more specific, because this tells you that whenever you're dealing with commutative sister algebras, given to you maybe abstractly, then there will always be some space that underlines the analytical structure that you have. Of course, the sister algebras are Banach star algebras, so they're not limited to the commutative case. And one can simply give the definition of a general a priori non-commutative sister algebra by saying that the sister algebra is a Banach star algebra, so an algebra with a norm, which is complete with respect to the norm, with an evolution that is compatible, and with this additional property that I highlighted before, that is that the norm of A star A is equal to the norm of A squared. There are many examples out there of non-commutative sister algebra, and one of the simplest ones is the algebra of n by n matrices. Of course, for n equal to 1, this is just a complex number, so that's commutative. And this is an algebra. This is a Banach star algebra, and it's also sister algebra if you choose the appropriate norm. And in particular, the algebraic structure is given to you by the usual vector space structure that you have on M and C. By involution, you take the conjugate transpose. The multiplication is just the usual matrix multiplication, and then the norm that you take is what is called the operator norm. So you look at the supremum overall vectors of norm 1 of the norms of A applied to those vectors. And if you compare this with the example of C to the power n that I showed you before, this is exactly the norm we had put there by seeing C of n as a subset of the n by n matrices by just putting them on the diagonal. Now you can extend Mn of C to infinite dimensions, and then you get to the algebra B of H of bounded operators on a Hilbert space. And this again, as a vector space structure, it's Banach space, but it's also Banach star algebra because it has a star operation, which is the operator adjoint. It has the operator norm, which is defined like the operator norm of matrices. Actually, the operator norm of matrices is a special case. And all those structures are compatible in the ways that I described before, and in particular, the sister identity is satisfied. Now, this algebra B of H is the quintessential sister algebra in the sense that every abstract sister algebra that may be given to you by relations or may be given to you in a very abstract way is actually a subset or a star subalgebra of the algebra of a bounded operator on some Hilbert space. And this is another foundational theorem in the study of sister algebra and operator algebras that is known as the Kepler-Neumark Seagull construction. And this tells you that whenever you're given an abstract sister algebra, then there will always be a Hilbert space H and some injective star homomorphism from the algebra A into the algebra of bounded operators on that Hilbert space. So in particular, this means that you can embed any given sister algebra into the bounded operators on some Hilbert space. And this will be a representation of your sister algebra. So now the general idea in non-commutative geometry and operator algebras, and if you want non-commutative topology, is that of looking at non-commutative star algebras of operators on some space, on some Hilbert space, as the algebras of functions on some quantized space or some non-commutative space. And this is not only a philosophical idea, meaning, okay, if the space were commutative, we would have a one-to-one correspondence, but if we drop the commutativity, what happens? That's a natural question to study, but it's also very effective because it allows you to treat spaces with singular actions and other pathological situations. So before we dwell into more details about the topic of this talk, I would like to introduce you to one of the most simple but at the same time interesting sister algebras to consider, which is the circle algebra. So we look at a compact topological space that it's a bit more interesting than a finite set of points, which is just a circle in a complex plane. So we just look at the elements in the complex plane that have distance 1 to the origin. Now you can define the sister algebra at C of S1, you can construct it, and this turns out to be the closure in a suitable norm of the collection of Laurent polynomial, which is more or less the underlying algebraic variety to the circle. So you just look at polynomials in psi and psi bar such that psi bar psi is equal to 1. Now this algebra admits a representation on a Hilbert space. This is not the GNS representation. GNS representation is a bit more pathological, but in this case, this algebra comes up with a nicer representation. And the Hilbert space we consider is the space of L2 functions on the circle, which can also be identified via Fourier transform with the little L2. So the Hilbert space of two-sided sequences indexed by the integers. And under this isomorphism, which is simply Fourier series or Fourier transform if you want, then the multiplication by one of the fundamental Fourier modes by e to the 2 pi I theta is actually mapped to what is called the bilateral shift. So whenever you, L2 of Z is a set of sequences, it has an orthonormal basis that is just labeled by integers. And when you act by multiplication by e to the 2 pi I theta on one of these basic functions, you just move up 1 degree. This is what happens when you do e to the 2 pi I theta times e to the 2 pi I n theta. You get to e to the 2 pi I n plus 1 theta. And then this operator U also has an adjoint that goes the other way. So it takes En and maps it to the En minus 1 vector. And this you can do in the two directions, and there's no obstructions to stopping because your sequences are two-sided. And then you can just identify C of S1, not anymore with the closure of the Laurent polynomials like we did, but with a sister subalgebra of B of L2 of Z of this bounded operators on this very nice and fundamental Hilbert space that contains the unitary U. So it will be a sister algebra generated by operator U that is unitary. So it satisfies U star U equal to 1, which is a bit like the relation that we have in the Laurent picture. Now, this is a commutative sister algebra, of course. As I said, the underlying space is S1, and we defined it to be the continuous functions on S1. But you can construct another sister algebra that in a similar fashion that will be non-commutative in this case. And that's a famous algebra called the Toeplitz algebra. So there, the Hilbert space is little L2 of n. So instead of looking at two-sided sequences, we now look at one-sided sequences. And you define again a shift operator that takes the basis vector labeled by n and maps it to the basis vector labeled by n plus 1. Now, this operator admits an adjoint, but this adjoint is not invertible because it only it gives you you can only go down by 1 if you're not already at 0. So T star of En is equal to En minus 1 if n is greater or equal than 1, and it's 0 if you're at the vacuum vector, as we would call it in quantum mechanics. Now, the fact that this adjoint is not invertible implies that when we look at T star T, we do get the identity because we have first applied T and then we apply T star, so we have space to go down. But if we look at T star, this is almost the identity up to the projection onto this the kernel of T star, which also happens to be the zeroth vector or the vacuum vector in our orthonormal basis. But you can do what we did before, and you can look at the sister algebra generated by this operator, or if you want, you can look at the smallest C-star subalgebra of the bounded operators on L2 of n that contains all the T and all its powers and all the powers of its adjoint. So this algebra will be indeed non-commutative because, as I said, T and T star do not commute. They only commute up to projecting down onto the vacuum vector. And now, from the fact that T and T star only commute up to projecting down to this vacuum vector, which is a rank 1 operator, you can guess that when you look at arbitrary powers of T and T star, those will commute up to compact operators, because we know the limits of finite rank operators are compact operators. And indeed, you get an extension of C-star algebra. So you get a short exact sequence where you have the algebra of compact operators on the Hilbert space L2 of n, which is also a C-star algebra, sitting inside this Toeplitz algebra. And then the quotient that you get when you quotient T by these compact operators is C of S1. And this is just telling you that the elements of T commute up to compact operators. And since when you quotient by the compact operators, you get something commutative, then you can compute the spectrum of that algebra, and it turns out to be the circle. What is interesting about this Toeplitz algebra is that it's non-commutative, and people sometimes call it the non-commutative disk. And this is not only an analogy, but it's really motivated by several aspects. And the first thing is that if you look at the spectrum of this algebra T, which you have to define as a set of pure states like we did before, then this spectrum is actually the disk. So it's really, that's topological space. And you can think of this extension here as a non-commutative boundary extension. So you know that in topology, you have all these boundary extensions. And here you have a boundary that is commutative, but whatever is inside that boundary is actually non-commutative algebra. So in the rest of my talk, I would like to build on this construction, this Toeplitz algebra construction, and define some algebras that are analogs of circle and sphere bundles. But before I do that, I'd like to point out that there is a bit of a general philosophy again in non-commutative geometry and topology, which is that because we know that topological spaces and C-star algebras are equivalent as categories, so there is an anti-equivalence of categories, then we can translate a lot of concepts from topology into the words, or if you want, into the language of operator algebras. So topological spaces correspond to commutative C-star algebras, and points, as we saw, correspond to pure states. But there are also other constructions in topology that you can make sense of in the operator algebraic world. For instance, the concept of vector bundle can be translated into the algebraic concept, a concept from ranking theory, of having a finitely generated projective module over a commutative C-star algebra. And this allows you to extend a topological K-theory, which is the study of equivalence classes of formal differences of vector bundles, into a similar theory, which is called operator K-theory, which is basically based on the notion of finitely generated and projective modules over arbitrary C-star algebras. You can also put more structure on this vector bundles. You can put a Hermitian structure, and then in that case, what you would get is not only a finitely generated projective module, but it will also be a module with an inner product that it's called, and this is what are called Hilbert modules in operator theory. And what I would like to discuss is how to fill in this dictionary by including two other types of topological constructions, which are circle bundles, and those will be translated into a class of algebras that are called Kunz-Pimsner algebras, due to the people that have been worked on them. And then I would also briefly go into the higher dimensional case and discuss sphere bundles and show that there is a similar construction to that of Kunz-Pimsner algebras that are called subproduct systems, or rather, maybe I should say Kunz-Pimsner algebras of subproduct systems. So let me now go into the setting of classical and non-commutative circle bundles. So we will just look at dimension 1. And then see what happens when we go up with our dimensions. So you already see this, it's not really readable at the moment, but we will look at the three-dimensional case. So here I have the Hopf bundle. Well, this is one of the pictures you can find at representation of the op bundle. The op bundle is one of, there are several op bundles. They're bundles of spheres over spheres with fibers of spheres. So they're famous sphere bundles. And the first one is what is used also in monopole theory, is the principal circle bundle with total space S3 and the base space, the two-dimensional sphere. So the way to look at this bundle, there are several ways of constructing it, but you can of course put S3, the three-dimensional sphere, inside C2, so the complex, I shouldn't say complex plane, so it's a two-dimensional complex vector space. And there you just look at the elements Z1 and Z2 in C2 such that they have Euclidean norm 1, so distance 1 from the origin. And on this set S3, which actually has a topological space structure, it's manifold, you can define a circle action, so an action by S1, and this is just a component-wise action. So you just take an element of norm 1 and a complex element of norm 1, and you multiply it component-wise with the points in your to the points of your sphere. You still get something that has distance 1 from the origin, so you get well-defined action. Now, this action is also free, so you can actually take a nice quotient, and then orbit space for this action is the two-sphere S2. So it's two-dimensional sphere, real two-dimensional sphere. So this bundle appears everywhere, especially in physics, because connections on the bundle describe magnetic monopole potentials. And of course, it's a bundle, so you have a projection from S3 into S2, but the way to look at this from an operator algebraic perspective is to dualize everything because of Gelfand duality. So instead of having a map between spaces, we look at a map between algebras. And this map between algebras will reverse its direction. So instead of having a projection between topological spaces, we have an inclusion of sister algebras. So we can include C of S2 as a sister algebra inside C of S3. And like we saw before, that S2 was the orbit space for the S1 action on S3. Now we can define a circle action on C of S3 and look at its fixed point algebra, and that will be C of S2, the algebra continuous function on the two-dimensional sphere. Now, what is interesting and what motivates, will motivate what you will see in a couple of minutes is that if you look at the coordinate algebra of S3, so you forget the norm, you forget that you are working with a sister algebra, but you purely look at an algebraic perspective, polynomial algebra, then this is an algebra that is of polynomials in 4 variables that commute, and that satisfies this identity Z1 bar Z1 plus Z2 bar Z2 equal to 1, which just tells you that these elements, the coordinate functions, come from coordinates of points that have a distance 1 from the origin. Now, if you look at this O of S3, this polynomial algebra, this has a very nice vector space decomposition. It decomposes over the integers, and each Ln is also a vector space. It's a module actually over C of S2, you will see. And it's the set of elements of O of S3 that transform under your circle action with a particular prescription, which is that if you use this circle action that you have on O of S3, then the element phi will be mapped to lambda to the minus n phi. And this will be true for every lambda in S1. So this is what in analysis is also called the spectral subspace construction, but it just tells you that this algebra of S3 admits graded decomposition. And each, of course, L0 is the elements that are invariant, because when you look at the formula I showed you before, lambda will be to the power 0. And this is just the coordinate algebra of the two-dimensional sphere, but each of these Ln is actually a bimodule from an algebraic perspective over this coordinate algebra O of S2. And it is a finitely generated projective bimodule. So it is a vector bundle. But there's more to this, because in algebra and actually also in quantum group theory, there is a notion of a principality of an action that admits an algebraic characterization. And the fact that you have a principal bundle here translates into an algebraic condition that tells you that the grading that you have, this graded decomposition, is what is called a strong grading, which means that whenever you tensor Ln with Lm, or when you multiply them, it would almost turn out to be equivalent, then you actually cover the whole of the n plus m component. And this is in general not true if you have a grading. You may always you always end up inside ln plus m, but you may not cover it all. And this is also equivalent to the notion of having that L1 is actually invertible as a module, which means that there exists another module, and in this case, it will be L minus 1, that whenever it's tensored with L1 gives you L0, and this happens when you do the tensoring in both ways. So this decomposition of the coordinate algebra of S3 into this invertible modules is what is called the Peterville decomposition. And in particular, it allows you to decompose the coordinate algebra of a circle bundle into the sums of powers of line bundles and completely characterize principal circle bundles. And it's very interesting. It's not a special feature of this Hopf bundle. It's a algebraic structure that many interesting sister algebras that appear in also in the classification program of sister algebras have. And so what I will describe now is how to make all these algebraic decomposition that I showed you that didn't have any norm involved into a well-defined operator algebraic construction. So for that, I need a bit of Hilbert module theory. And as I said, Hilbert modules are the object in the non-commutative geometry dictionary that allow you to extend to operator algebras the notion of having Hermitian vector bundle. So they generalize the notion of Hilbert space. The idea is that instead Hilbert spaces are over the complex numbers, but here instead of looking at complex numbers, we look at inner products that have values in a sister algebra. So a Hilbert module will be a pair E and an inner product where E is a module over the sister algebra B, but it also has an Hermitian b-valued inner product. So you can imagine the axioms of an Hermitian b-valued inner product are the same as the ones for the usual inner products. The only thing is that when the positivity condition is that, sorry, maybe I should call it psi. That whenever you look at the product of psi with itself, this has to be positive. And what does positive here mean? It means that it's positive as an element of a sister algebra. Which means that it's of the form B star B for some B. But once you fix this, once you make sense of what it means to be positive definite in the sister algebraic setting, you can also define a norm like you would do normally. So you define the norm of one element in your module to be the inner product of that element with itself. This gives you an element in the sister algebra. And then we know that sister algebras have a unique norm. So to get a complex number out of that, we just compute the sister norm. And this shouldn't have the square, I'm sorry. So these Hilbert modules are really a generalization of Hilbert spaces. They're more subtle because the notions of orthogonal complements are ill-defined, but they allow to extend the whole theory of Hilbert spaces to them. So it also makes sense to consider their direct sum, their tensor products, and also to consider operators on them. So the adjointable operators will play a very important role, and those are defined as linear maps from a module to itself. Well, you can also define it in principle if you have two different modules, such that they admit an adjoint. And the reason why we do this is because that's the only way we can do it. We don't have a Riesz representation theorem for Hilbert modules. So we cannot first look at bounded operators and prove that they're all adjointable, because that's not true. So adjointable operators will automatically be bounded in Hilbert modules, but the converse direction doesn't hold. So this is the correct notion to consider. And this is the one that gives you back the bounded adjointable operators on a Hilbert space when you use a Hilbert space instead of a Hilbert module. So you can also define the dual of a Hilbert module, and you do it again similarly to what you would do in a Hilbert space setting. There again, you would use the Riesz representation theorem, and here instead, you define the dual to be the collection of elements in the bound that are bounded adjointable homomorphism from E to your coefficient algebra that can be represented as inner products. So not all of them can, but the ones that can will be your elements of the dual. Now, to give a generalization of the notion of line bundle to the non-commutative geometry world, we want to mimic a bit what we saw before. So remember that before we saw that our modules were invertible in the sense that there was another module that we could tensor them with on both sides that will give us back the zeroth module. And there is a similar notion for Hilbert modules, that's that of self-Morita equivalence. And we say that the finitely projective Hilbert module over a unit of sister algebra is a self-Morita equivalence is if whenever we tensor it with its dual module on both sides, so from the right and from the left, we get a module that is isomorphic to the coefficient algebra be seen as a Hilbert module. Now, the reason why these self-Morita equivalences are called non-commutative line bundles is that they generalize line bundles. So whenever your algebra B, your coefficient algebra is commutative, then the module of sections of any Hermitian line bundle on that space is a Hilbert module, and it turns out to be invertible in the sense that I have described here. So any modules of sections of Hermitian line bundles is a self-Morita equivalence. So it's a Hilbert bimodule that happens to be invertible. So what I will now describe is a way of constructing a sister algebra out of an invertible bimodule in a way that the sister algebra you obtain is the total space of a circle bundle. And this construction resembles a lot the one we saw when I introduced you to the Toeplitz algebra, and the Toeplitz algebra is actually a special case of this construction. So we start from E. This in general works for any correspondences, well, for any bimodule that is finitely generated and projective. So we look at the module that is obtained at the direct sum of your coefficient algebra B, that you should think of that as like a base space of your line bundle. And then you look at all the powers of tensor products of E with itself. So this gives you a well-defined Hilbert module, and you can define operators on this Hilbert module by just tensoring elements in the end tensor component. So if you have an end tensor, you take another vector in E and you tensor with it from the right. And this gives you an n+1 tensor, and in particular, it defines an operator that is well-defined on this direct sum module. And when you're acting on the coefficient algebra, so on the zeroth component, you just multiply with that, use the right module structure to multiply the vector and the coefficient together. Now, operators of this form are adjointable operators on this module. And in particular, it makes sense to consider the sister algebra of the algebra of adjointable operators that contain all the operators of this form. If the module you start from comes from a line bundle, so it's what is called a self-Morita equivalence bimodule, then you can also do a construction that is two-sided. So you can define also negative powers of E by using the dual module. So you look at the direct sum of these ENs that I wrote here. These ENs are equal to tensors of E with itself n times if n is positive. E0 is equal to the coefficient algebra, and En for n negative is the nth tensor of E star with itself. So this gives you a grading over the integers like the one we saw in the construction of the Hopf bundle. And on this module, you can also consider operators, but this time they will be bilateral because they will allow you to go from component n to component n+1, and their adjoints will do the opposite. So it will be exactly the same as what happened for the Toeplitz algebra case. You have operators that just map a degree n element to a degree n+1 element, and their adjoints go the other way around. And now you can define the Kunz-Wimser algebra of E of this module to be the smallest C-stars of algebra of all the algebras of bounded adjointable, of the algebra of all bounded adjointable operators on this module that contains the bilateral shift. So we're doing exactly what we were doing before. We have an algebra here on the previous slide. We have this algebra that is generated by a unilateral shift because there's only so much we can do with the adjoint. We can only go back to B, and there's no negative part. But we also can look at the module that has two sides, as a positive part and a negative part. And on this module, we have also shift operators. But this time their adjoints will behave much better because they will go both ways. And now if you look at the sister algebras you get with these two construction, you actually get an exact sequence of sister algebras where you have the algebra of compact operators on the one-sided module, sitting inside this Toeplitz algebra of the one-sided shift. And then the quotient will be an algebra that is generated by a two-sided shift. And if you do this for the direct sum of the complex number, so for infinitely many copies of the complex numbers, then you get exactly, I'm not sure, yeah, the extension that I showed you before, where you had L2 of n, which is infinite. It's also isomorphic to the infinite sum of the complex numbers for every degree. Then you have this Toeplitz algebra that is non-commutative because the shift is unilateral. And then you have a quotient algebra that is generated by a two-sided shift. And so what I would like to explain to you is that this construction with these two algebras sitting into an exact sequence where the ideal is the complex, is an it gives you a huge class of sister algebras that you can interpret as principal circle bundles over another algebra, commutative or not. And indeed, because both TE and OE come from a grading, you can endow them with a circle action, and you can look at the fixed point algebra for that circle action. That's also sister algebra. And whenever you have started from a module that was invertible, so there was what we call self-Morita equivalence, but there was like a line bundle that behaved exactly like the modulo section of a line bundle, then the fixed point algebra for the action is actually the coefficient algebra. So this tells you that your sister algebra is a principal bundle in the operator algebraic sense, if and only if it's constructed out of a module that is a line bundle in the operator algebraic sense. And this we proved in, well, some years ago in a joint paper with Jens Kohl and Giovanni Lanni, is that all the Pimster algebras of self-Morita equivalence by modules are quantum principal circle bundles. So they satisfy the definition of a quantum principal circle bundle that is given in the OP algebraic world. And there are many examples of deformations of classical circle bundles, in particular the ones that come from a quantum groups deformation. All those that have a principal circle bundle structure, when you look at the sister completion, behave exactly like those Pimster algebras, and they can be constructed as such. So this is the analogy we discovered between this construction of shift operators on modules and the classical construction of a line bundle and its associated circle bundle. The other interesting thing in this construction is that because we have an extension of sister algebras, operator K-theory gives you a 6-term exact sequence in operator K-theory. And this operator K-theory, as I said, is the generalization of topological K-theory, and it recovers the classical topological K-theory groups whenever you input a commutative algebra. And the sequence that you get contains a map in the middle that we were very interested in, and we were very interested in recovering somehow, which is this, sorry, my pen is not reacting. Okay, now it is. This 1 minus x. So we are multiplying elements in the K-theory group of a coefficient algebra with 1 minus the bundle we started from. And this is exactly the same form that another sequence in algebraic topology has. This is the Gizen sequence for principal circle bundles. And there you also have a map that is 1 minus a class, and the class happens to be the class of a line bundle. So what we observed is that the analogy that we could point out between non-commutative circle bundles and classical circle bundles was not only at the level of the coordinate algebras, or if you wanted the sister algebra. So was not only at the level of topological spaces, but was also there at the level of generalized cohomology theories for topological spaces. So whenever you would get this exact sequence classically, because you had a principal circle bundle coming from a line bundle, you would get exactly the same exact sequence in the dual theory, so in operator K theory instead of topological K theory. All right. So in the last 10, 15 minutes of my talk, I would like to explain to you how it's possible to go from this very nice construction this very nice analogy also that you have for line bundles to the setting of different type of vector bundles and sphere bundles. And in particular, I will be aiming at constructing out of a vector bundle a sphere bundle of the appropriate dimension. So let me go back to the templates extension that I showed you before. So this extension that gave you the algebra, the universal sister algebra generated by partial isometry as an extension of a commutative algebra, the algebra of functions on a circle by compact operators. So this extension admits several generalizations. One of the generalizations we just saw, it was that of a Kuhn-Wimser algebra of correspondence that allows you to move somehow from circles to circle bundles. So this is, if you want to interpret it this is from circle, from S1 to S1 bundles. But there is another way in which you can extend the templates extension. You can go from S1, which is an odd sphere, one sphere, to all the odd spheres. So from 1 to, let's say, 2D minus 1. And this was something that was done in the 70s by Arvidsson. So he constructed extensions of sister algebras for odd dimensional spheres. And in particular, he realized that there was a short exact sequence where the ideal was compact operators on some different Hilbert space. This is called the Drury-Arvidsson Hilbert space, and it's a generalization of the Hardy space. The quotient in the extension is a continuous function on an odd dimensional sphere. And the algebra in the middle, it's also an algebra generated by a shift, but it's actually by a collection of shifts. And all these are examples of another construction, which is Kuhn-Wimser algebras of subproduct system. So you may already guess from this idea that if from the templates extension you can go to S1 bundles, then maybe if you could extend this and glue things together, then you could go to sphere bundles with fibers, the odd dimensional spheres. So let me first explain this Arvidsson extension to you. So we need this Hilbert space that I just mentioned, this Drury-Arvidsson space. And we start from D commuting variables, and we look at the space of polynomials in this D variable. Now we can put, you can write the monomials in the space of polynomials in a compact way. You just take a multi-index alpha 0, alpha d minus 1, and you write z alpha to be z0 to the power alpha 0, z1 to the power alpha 1, and so on until zd minus 1 to the power alpha d minus 1. So these are the monomials in this collection of polynomials. And now you can define an inner product on this collection of polynomials by just saying that z alpha and z beta are almost always orthogonal, except when alpha and beta are equal. And in that case, you define the norm of that vector to be given in terms of multinomial multifactorials. The reason why this norm is like that is because we are using this identification that you probably all know from representation theory of algebraic geometry, that polynomials correspond to symmetric tensors. Homogeneous polynomials correspond to symmetric tensors in the same variables. And this Drury-Arvidsson space, H2 of D, is really a bit like the Hardy space. So it can be identified with a space of holomorphic functions on a D-dimensional ball that have a power series that satisfy that following condition, which is that it's, the norm is bounded. And clearly, it is this Drury-Arvidsson space through the identification that I mentioned before between homogeneous polynomials and symmetric powers is isomorphic to a famous Hilbert space that appears in physics, which is the symmetric Fock space in D particles. Now, on this space, we can consider what is called the D shift. And this is a generalization of the shift operator that I explained to you before. So this will be a D tuple now of a multiplication operator. So we multiply in each variable. And you can identify this through a unitary transformation with the compression on the shift of the full Fock space. So you shift in each of the directions of the component and make you up your tensor. And this shift satisfies several nice properties. It is commuting to begin with. So Ti, Tj, and Tj, Ti are equal. But when we look at the adjoints, and we look at the sum of Ti, Ti stars over all the i's, we get exactly what we had in the one-dimensional case. We almost get the identity up to a projection onto the vacuum vector or the zeroth component of our, well, it's just polynomials that are constant. And moreover, this operator is essentially normal, meaning that the Ti's and the adjoints of the Tj's almost commute. And they commute up to, they do happen to commute up to compact operators. And this is just a formula that tells you that. And here is the number operator. This is just that operator that tells you in which component of your symmetric Fock space you are living. But this means that their difference is a compact operator because n is unbounded, but 1 plus n minus 1 is compact. And this again tells you that all the elements of the C-star algebra generated by the shift are almost commuting. They commute up to compact operators. So the quotient that you would get by taking out the component that comes from the compact operators will be a commutative C-star algebra. And it turns out that you can prove it. This was proven by Arvidsson in '98. You can compute the spectrum of the C-star algebra, and it's a 2D minus 1 dimensional sphere. So again, you see this triplets algebra here. This time it's generated by D directions as a ball, a non-commutative ball whose boundary is an odd-dimensional sphere. So again, we get a classical dimensional sphere as non-commutative boundaries of triplets algebras. And this is what is an example of a subproduct system extension. So what we did in our recent work with Jens Kade from University of Odense is trying to use this construction to obtain C-star algebra that comes with an SU2 action instead of an S1 action. So our goal is to extend the notion of a principal circle bundle to higher dimension. And we thought, okay, the next natural one is to look at a three sphere. And a 3-sphere also happens nicely to be a group. It's the group SU2. So we're trying to give an operator algebraic characterization of C-star algebras that come with an action of the group SU2. So for every positive integer, we start from one of the fundamental representation of SU2. You know that those are classified by positive integers, or if you want a half integers, if you're a physicist, and those represent on the tensor, on the symmetric tensors. So out of each representation, we define what we call the determinant. And that's a space of elements that are invariant in H times H under the diagonal action. Oh, I should write H here, sorry. I moved. So Ln is equal to H here. And we constructed an inductive family of Hilbert spaces where we started with E0 being a complex number, E1 being our representation space. E2 was the complement of the determinant, and then, oh, I'm really sorry. And then we went up inductively to construct all the other fibers. And by this, we constructed a Fock space. So we mimicked exactly the old construction. And on this Fock space, we consider triplets operators. Now, this triplets operator behave a bit more complicated behavior here, because as you know from the Krebs-Gordon theory, when you tensor elements in two representation space, you don't get in the next representation space, you get in a direct sum of representation space that range from their sum to their absolute value of their difference. So what the way we fix this is by projecting down to the relevant component. And then we define a C-star algebra associated to this family of Hilbert spaces to be just a C-star algebra generated by all those shift operators. In our case, this algebra comes with an action of the group SU2, and it also gives you extension of sister algebra by the compact operators. And this extension also happens to be equivariant with respect to the SU2 action. So what we proved is that this tuplets algebra has very nice K-theory groups. It's actually KK equivalent to complex numbers. So if you want, it's a bit boring. But the consequence of this theorem that we prove is that we do obtain an exact sequence in K-theory. And this exact sequence really looks like the exact sequence that you would get for a three-dimensional sphere bundle. So it has a map in the middle, and this map is like the one I showed you before. That was 1 minus the class of a line bundle. And here instead you have 1 minus the class of a rank 2 vector bundle plus the class of a line bundle. So this is what is called the Euler class of a vector bundle. It's an alternating sum of classes. And it comprises of 3 terms, exactly like we would expect classically. So this allows me now to conclude my talk with a summary. So by looking at sister algebras, you can reformulate problems in geometry and topology. And in particular, what we observed in earlier work was that if you use the non-commutative geometry dictionary, then this class of algebras called Kunz-Wimser algebras are really a model for circle bundles, meaning that when you start from an invertible module, you get an algebra with a principal U1 action. And if you start from an algebra with a principal U1 action, you get, you can realize it as a Kunz-Wimser algebra. And then the analogy goes forward to computing K-theory groups with a sequence that it's like the sequence you would expect for a line bundle. And the same is true if you try to go a bit higher up and you look at SU2 actions. Of course, what we did here is just a very simple example coming from representation theory, but what we observe is that these algebras of subproduct system have a very nice behavior that seems to be suitable to encode algebras with spherical symmetries. And of course, we're still working on extending these to really sphere bundles. What I showed you before were just SU2 representations. But of course, having gotten this exact sequence that has exactly the same classical form is a good motivation for us to continue in this direction. And I would like to thank you very much for your attention, and I'm happy to answer questions.
Thank you very much for your talk. Are there any questions from the audience?
So thank you very much for your talk. I have some questions. So the first thing is, so the tuplets algebra is like the derivations on the circle. Is that right?
Sorry, can you say it again? Is like?
So this tuplets algebra is like derivations on the circle.
Yes, so you can see it like that as well. It's like derivations on the circle, yeah.
Yeah, and then my question is, can I extend to get the Bilateral algebra, that is the central extension?
Oh, that's a very interesting question. I have not thought about it, but yeah. I really don't know how this connects with that, because of course there are different type of extensions of algebras. I mean, here we're in the C-star setting, and the Bilateral algebra is a different type of algebra. So I don't know how this relates to that, to be honest. But that's certainly something worth looking into.
Okay.
Thank you.
Is, normally on circle bundles, we can consider circle bundles with connection. So do you have any analog that reproduce what connections are?
Yeah, so here there are no connections at the moment, but there is a notion. So the fact of having a principal bundle translates into an algebraic version of a notion of connection that is used on quantum group theory. So I think that could be the link to what you're asking.
Okay.
They're called strong connections, but I'm not sure if.
Okay, thank you. And then another question is, instead of going to higher spheres, you can go to gerbs.
Yes, so of course, yeah, this you can also do, yes. So the way we want, so the approach we're taking now is different in the sense that whenever you have a vector bundle with an Hermitian structure, you can construct a sphere bundle out of that. Just look at the ball bundle, then take the boundary of the ball bundle, and that as a sphere bundle structure. And then K-theory exact sequences tell you that you would have an exact sequence with an Euler class in the middle. So this is the type of construction we were after when we started this paper. But of course, you could go into gerbs and other, to classify them, because of course, you don't have you need a different type of cohomology theory. But sister algebras are a bit poor with respect to cohomology theory. So the only one that they have several cohomology theories, but the one that that works the best at the moment is K-theory. I mean, you have other types of periodic cohomology, cyclic and auction. So I don't know how I would generalize the notion of gerb to a non-commutative algebra. Thanks.
There is also a question from someone in the online audience. Raise their hand. Or not anymore?
Like, we cannot hear you.
Can you hear me now?
Yes.
Good. Hi, Francesca. Thank you for your beautiful talk. I was wondering if you have thought of, if you have a sister algebra that is the convolution algebra of a Lie groupoid, what do these circle bundles and sphere bundles correspond to?
Okay, that's a very good question. So there is some work that tells you that if you have a Lie algebra, that's not really Lie. So if you have a groupoid sister algebra of an étale groupoid, so the ones that have discrete fibers, then those are all, those can always be realized as Kunz-Pimser algebras. But that's of course because whenever you're in the étale category of groupoids, you have you have this kind of discrete fibers, and this allows you to define an integer grading. But if you would have a different type of groupoid sister algebras that don't admit this graded structure, I'm not sure how they would fit into this, if they would fit into this framework. But this is a question that I've been asked by other experts on groupoid sister algebras. And there is clearly a connection between groupoids and Kunz-Pimser algebras, also because many algebras that have a groupoid model that come from dynamical systems admit also Kunz-Pimser model, but this is very often in the étale category. So when the fibers are of the range and source map are discrete. So for general Lie groupoid, it's very open.
Great, thank you.
Any more questions or comments? Okay, I guess it's not the case, so we can thank Francesca again. And yes, this was